Today we will be presenting Corollary 1.24 from Geometry for College Students by
First, we need to get a few definitions out of the way before we explain our theorem. First of all, a secant line is a line which intersects a circle at two given points. A tangent intersects the circle at one point at which the circle and the line intersect is the point of tangency. The tangent line is perpendicular to the radius at the point of tangency also. An arc is a curved line that is part of the circumference of a circle. We can denote this arc as AB. A chord is any line segment joining 2 points of a circle. We can say that a chord is an interval of a secant line.
All right, we have some more definitions. So on any given circle, we can draw a center. We'll call that point O. And let's draw a line from the center to the exterior of the circle. Let's draw two, actually. And label the end point of 1A and the end point of 2B. Now, this is what we call a central angle. That is, any angle centered around the center of a circle. And we can say that the measure of this case, angle AOB, is equal in degrees to the arc AB. Now, what does that mean? Well, we can say that there are 360 degrees in a circle. That corresponds to the entire full arc length of the circle. So if we cut a little piece of that, we can say that that's got to be some portion of 360 degrees. So we measure this in arc length. And this is what we call subtended arcs. So this is an example of, this central angle is an example of an interior angle. That is an angle inside the circle. Now, if we draw a chord from point A to, let's say, point C, and another chord from point A to point B, then angle CAB also is an interior angle because it is on the inside of a circle. So we can say that angles AOB, the center angle, and angles CAB are interior angles because they lie on the interior of the circle. Now let's draw a random point P, and we'll run that through A to C. And then we will draw another line, tangent. Just call that point D. Now, we can say that angle P is an exterior angle because it lies on the exterior of the circle.
Let's draw two parallel lines, AB and CD, and transversal line PQ. The intersection of AB and PQ is labeled E, and the intersection of CD and PQ is F. Now we can say that angle PEA and angle EFC are corresponding angles, and they are equal to each other since AB is parallel to CD and PQ is transversal. And then we say that angle AEF and angle EFD are alternate interior angles, and they are also equal because AB is parallel to CD and PQ is transversal.
Okay, let's review theorem 1.4, which states an exterior angle of a triangle equals the sum of the two remote interior angles. Okay, we want to show that angle ACD equals angle A plus angle B. First, draw a parallel line to AB and label its endpoint P. Angle A equals angle ACP since these are alternate interior angles for parallel lines AB and PC. Angle B equals angle PCD since they are corresponding angles. Therefore, angle ACD equals angle ACP plus angle PCD, which equals angle A plus angle B. Hence proved.
All right, so now we're going to prove theorem 1.16. So we have a circle, centered on point O. And we draw a point P on the exterior. Let's draw a line through the diameter. This means from point P to point O, straight on to the other side of the circle at point A. Now let's draw a line from point P to another part of the circle. We'll call that M, point B. And then let's draw another line from B to the center. Now, because lines BO and PO go from the exterior circle to their radius. Therefore, their side length is equal, which makes triangle POB isosceles, which also means that angle OPB is equal to angle OBP. So, as we said earlier about central angles, we can say that angle AOB is central and therefore equal to its arc length. So we can say angle AOB equals in degrees to arc length AB. Now, we can see that angle POB is supplementary to angle AOB, which means that they add up to equal 180 degrees. So we also note that the angles in triangle A or POB must add up to be 180 degrees. So we can say 180 degrees equals angle OPB plus angle OBP plus angle POB. And we already established that OPB and OBP are the same. And for short, we're just going to change that to angle P. So we can say that 180 degrees is equal to 2 angle P plus angle POB. Now we already know that angle AOB plus angle POB must be supplementary, which means they must equal 180 degrees. We can say that angle AOB plus angle POB is equal to 2 angle P plus angle POB, because that's equal to 180 degrees too. So we see we have angle POB on both sides, so we can get rid of that and just break it down to angle AOB is equal to 2 angle P, and since we already said that angle AOB is equal to the arc length, we can say 2 angle P equals in degrees to the arc length of AB, or in other words, angle P is equal to 1/2 AB, the arc length of in degrees. So in other words, the inscribed angle P, inscribed meaning that it's on the point, an actual point on the circle, is equal to 1/2 its subtended arc. All right, now we're looking at theorem 1.23, which states the angle between a chord and the tangent at one of its endpoints is equal in degrees to half the subtended arc. Let's start with the circle we had last time, and we're going to make this chord the diameter. So we're going to go A at the top, O is the middle, P is the bottom. All right, we got that. Now we're going to draw a line T that passes through point P. This line is tangent to the circle, and point P is the point of tangency. Now we know from earlier that between the radius and the point of tangency is 90 degrees. All right, so now we're going to draw a point Q here on the outside circle. And let's draw a line from Q to P. Okay? So just by looking at this, we can see that angle APQ and angle QPT add up to be 90 degrees because they make up that point, or that entire angle between the radius and the tangent line. So we can go ahead and write that out here. Now we can rewrite this to say that angle QPT equals 90 degrees minus angle APQ. Now, theorem 1.16 states that angle APQ should be 1/2 the subtended arc AQ. So we can rewrite it as angle QPT is equal to 90 degrees minus 1/2 AQ. Now we can do something interesting. We can look at that equation and do a bit of factoring. Let's pull out the 1/2. So now we have angle QPT is equal to 1/2 times 180 minus the arc length AQ in degrees. So what does that look like? Well, we know central angles are equal in degrees to their subtended arcs. So angle AOP is a central angle, and since it's the diameter, it's equal to 180 degrees. Now we can put this back into our equation and replace the 180 degrees with the central angle AOP, which is equal in degrees to the arc length AP. Now we have the arc length AP minus the arc length AQ. So what does that equal? That's right, that's just QP. So that means that we can replace that entire side of the equation with just 1/2 arc length QP. Of course, this is measured in degrees. And there you have it. Theorem 1.23. The angle between a chord and the tangent at one of its endpoints is equal in degrees to half the subtended arc.
Finally, we have reached corollary 1.24, which states that the angle between a secant and a tangent meeting at a point outside a circle is equal in degrees to half the difference of the subtended arcs. So if we draw a circle and draw a tangent QP, which intersects the circle at point C, and we draw secant AP, which intersects the circle at point B, we can also draw a chord AC, and I'm just going to draw that with a dotted line. So essentially what we want to show is that angle APQ is equal in degrees to 1/2 CA minus 1/2 CB, and that's arc CA and arc CB. So first we can say that angle CAB is equal in degrees to 1/2 of arc CB because angle CAB is an inscribed angle. We can also say that angle ACQ is equal in degrees to 1/2 of the arc AC by theorem 1.23, which was just proved. We can use some algebra and say angle ACQ is equal to angle CAB plus angle APC, which was mentioned in theorem 1.4. And then rearranging, we can say angle ACQ minus angle CAB is equal to angle ACP or APC. Now we know that angle ACQ is equal in degrees to 1/2 of AC, and angle CAB is equal in degrees to 1/2 the arc CB. So we can just use some substitution, and then pulling out the 1/2 in front, we can say that angle APC is equal in degrees to 1/2 AC minus CB. And this concludes the corollary.